Chapter 9 introduces us to a little bit different idea. If you remember, when we started last couple chapters, 7 and 8, we started off with the idea of saying, okay, we have a force, we exert a force on a mass, and it moves, and so I wanted to know kind of what effect is my force having on the mass. And so we said, well, maybe force times distance would give us something, and that gave us the idea of work. We later realized, well, it's not just force times distance, it's force in the direction of the displacement, so it's only a component of the force. And furthermore, it's possible the force could be variable, and so we ultimately came up with the idea of integral f dot dx, and that was work. And we said, what is work? Because force is equal and opposite, then if you do work on something, it does negative work on you. And so when you do work on something, you then imbue it with the ability to do work on something else. And so it's almost as if we're storing work in there. And this led to the idea of energy. We now realize work is in fact change in energy. It's not really that we're storing work, but rather we're storing energy, and the more energy you have, the more work that you can do. And so this was basically chapters 7 and 8 was taking all this sort of stuff right here and putting it into effect. Let's go back. Got an object here, exert a force on it, and what we did before was we said, well, we multiplied force times distance. Well, we also know the longer the force is applied, the more likelihood it's going to do something. For example, if I apply a force on an object for 10 seconds, or I apply a force on the object for 20 seconds, if it's accelerating, it's going to accelerate for twice as long. And so that means it's going to be moving farther. It means it's going to be moving faster. And so there's also the idea of time. So if force times distance was equal to something interesting, would force times time be worth studying? Well, that's a good question. So we think about it. We say we have a force, we have multiply times time, but well, wait a minute, it is also possible that the force could be variable. So again, you want to do the integral, you want to do the summation of force delta t, take the limit as the delta t gets really small, and then that's going to give you something. And so that's going to be giving something that we call an impulse. Okay. And so now we're going to have an impulse. We're acting on something and we give it an impulse. Okay, so we use the letter J for impulse. Okay, well, this is an integral. So integral of f dt, well, time is a scalar. Vector times scalar is a vector. So we would say the integral f dt is going to be giving us this impulse, and the impulse is going to be a measure here of this whatever effect we're having. Well, by the same token, then we look at this and we say, well, we knew that integral of f dot dx was work for every force and equal and opposite force, so work ended up being the change in some conserved quantity, energy. Well, up here, the impulse for every force is an equal and opposite force, so that means if we give an impulse to one object, it takes the impulse from something else, and so this is going to be a conservation of something too. And we use the letter small p to indicate the change in whatever this is. Okay, and in fact we call that momentum. We do not use m for momentum because m is being used for mass. So we say, what's this momentum thing? Well, integral f dt is going to be equal to the change in momentum. So that's the integral of dp. Okay, remember integral dp is going to be p final minus p initial. So what is the integral f dt? Okay, well, right away we look at this and say, wait a minute, we could actually say here that f dt equals dp, so f equals dp dt. So that means that the rate of change of momentum is your force. So now we actually have an idea what force is. Force is rate of change of momentum. So if you're changing the momentum of something, you're exerting a force on it. And so this is an unbalanced force right here. And so this gives us an idea. And then we say, well, we still want to find out what is this, how do we find P? Okay, so we know what dp dt is, that's F. Go back up here. So delta P, that's going to be P final minus P initial, and that's integral F dt, from initial to final. Okay, so P final minus P initial, integral F dt, that's the integral of ma dt, because F equals ma. Well, if we assume that the mass is constant, now later on this chapter, we're going to take mass being constant away and allow mass to vary. Okay, that'd be like a rocket. So this is integral a dt. Well, we know that a is dv dt. So the dt's cancel. So we have integral m times integral dv. Well, that means P final minus P initial is going to be MV final minus MV initial. So the delta P is going to be equal to delta of MV. That would suggest that momentum is mass times velocity. And so that's our expression for momentum right there. So that's the derivation really for the first for the part of this chapter. Now if you look in the chapter, I'm taking this in a slightly different order than how the book does it. The book starts off with the idea of center of mass. I'm going to end with that. So I'm going to do the impulse and momentum stuff, and then do center of mass at the end, because that feeds right into the next chapter. So momentum is mass times velocity, and so that means that impulse is the change in momentum. And so when we have impulse, we're changing momentum of something. Whenever I think of impulse, I think of Star Trek and impulse engines, which would change the momentum of the starship. And so, and again, in rocketry, we talk about the impulse of a rocket engine, or specific impulse of the fuel. And so these are all concepts that relate to change in momentum.